All right. Game time. 2:15 here, so let's go ahead and get started with things. The first thing that I do want to cover is not what we see on the screen, but it's actually something that we looked at last time. So I think what happens here is that talking about this, I was describing a lot of these details, but I think without having the lab in front of your faces already and having read through the lab and been working on the lab and everything else, I don't think that stuff stuck as well as I had intended it to. So I did want to talk about this one more time, I'm not going to go over all of these details one more time, but to say that once you have taken a look at the lab and once you've gotten started working on the lab, what I'm going to recommend, those mass calculations are the biggest, most difficult part of this entire thing. If you can get the mass calculations, the rest of it is just a couple other centripetal force and then velocity from that. You know how to deal with those things. But in thinking about what to do about the masses, I would highly, highly, highly recommend, now that you've looked at the lab a little bit, to go back and look at this slide in particular during the lecture. I know I talk about conceptually what's going on with this one right here, but in the lecture itself, I talk about exactly what you're expecting to find for the expression for what you need to find the interior mass and where that changes partway down the line to becoming essentially a fixed value from then on out. So I wanted to highlight that one because I know I've been recommending a lot of people just go back and watch this one again because it is, I've, especially over email, especially over text and everything else like that, it is a much more effective way to see. I described it better in the lecture than I ever will be able to in an email. So that's why I was recommending this one so much. I'm still more than happy to answer some questions after class about these as well. But if you're still a little bit fuzzy on what to do about the mass, I would recommend watching this one more time. Now that you've got the context of the lab, I think it will click a little bit better, make a little bit more sense. So let me go ahead and dive into the material from today, though. And if we do have more questions over the lab and everything else, I'll just, at the end of it, today's going to be a little bit short anyways. We'll end a little bit early, so I'll have plenty of time afterwards to go over some lab details if you guys need it. So, the name of the game today is harmonic oscillator, something very different from what we've been talking about, at least last chapter. But let's do a recap of the course. We looked at things moving in lines. Then we looked at things moving across two lines. Then we looked at things moving around a point. Then we looked at how things essentially affect other things that are nearby, right? Normal forces, friction forces, things like that. Then we looked at sometimes things can affect really, really far away things. Even if they are 5,000 light years away, gravity still works. All of these things have been how we have described motion so far. But we're not actually done. If we remember way back to that picture, the different types of motion, we have covered 3 out of the big 4 at this point. Remember, we had linear motion, we had projectile motion, we had rotational motion, and now we are finally covering that 4th, oscillatory motion. And that means something that goes back and forth and back and forth and back and forth and back and forth forever and ever and ever. So let's talk about that. The name of this is simple harmonic motion. Oftentimes you'll see this abbreviated as SHM because, well, it's kind of a long name on its own. But those 3 words, what do they all mean? Simple, hopefully, right? Motion, just what we were talking about before. Harmonic is the new one. And you might have heard of harmonic in a few other, it's not harmonica, that's a little bit of a different thing. Harmony, kind of close. But harmonic, generally speaking, means repeating patterns. A harmonic oscillator, simple harmonic motion, means that it's going through the same motion over and over and over again. It's not changing where it's at. It's not going from A to B. It's moving back and forth at the exact same pattern every single time. Most of the time, what is our favorite repeating pattern? What's our favorite repeating pattern? Sine. That's the correct answer. A lot of people in the last lecture were trying to tell me that, like, weekends, sleep, none of that nonsense, right? We love sine waves. Sine waves make up almost literally everything. And I don't really even mean that as hyperbole this time around. I mean, like, when you're talking about hearing my voice right now, right? The sound that I'm emitting that is going through all these different places, I emit sound that's made up of a bunch of sine waves. It shakes the microphone. That shakes like a sine wave. It transmits electricity through AC circuits, which means alternating current, which means sine waves. It arrives to you, sine waves as a signal to more sine waves to reach your ear. Your eardrum oscillates as sine waves. The sunlight that you feel on the outside is a whole bunch of sine waves. If you want to talk about the vibration of atoms that make up temperature, sine waves. Am I getting the point across? They show up literally everywhere. Simple harmonic motion is one of those almost universal kind of concepts. It shows up in just about everything that you could possibly want to do. And luckily, we're already pretty familiar with what that motion looks like. So first things first, we need to figure out what is actually going to be causing this kind of motion. And there's actually a small variety, of course. This variety of things that I have just listed out are all sorts of different places that sine waves can show up. But we want to focus on a really easy to describe one that we're already pretty familiar with. Springs, right? So let's imagine here, we've got a frictionless track, we've got a spring, we've got a mass on the end of it, and what we're going to do is we're going to attach this thing. Initially it was at equilibrium. We're going to drag this block out just a little bit and release it. What does it do? Well, how we figure that out is determined essentially by what forces are acting. We're only looking at the x direction here. I really don't care what happens in the y direction. Let's focus on x. So I pull this thing out. We might remember that the actual force from a spring is negative kx, right? And so if we're just looking for the magnitude of the spring force, kx is sufficient. But here, we are a little bit more focused on the direction. The direction is pretty important, so we're going to say, all right, well, negative kx, and what is that trying to say? That when we pull out the block to a positive direction, it's got a positive x position now, the spring wants to pull it back. It wants to pull it back to 0. So my position right here is going to go negative of what my position is. Then I release it, right? So it's got a force pointing to the left. It moves over to the left. It goes over. It compresses by some amount. Now its position is negative x. The force flips to being in the positive direction. It travels a little bit more, slows down to a stop, and then comes back the other way. And it does that back and forth and back and forth. It oscillates around this, what we have called x is equal to 0. This spring force is acting as what we would call a linear restoring force. Again, another 3-word phrase, a little bit complicated. Let's break it apart piece by piece. Linear means it depends on x. That's an eraser. X, not x squared, not square root of x, not 1 over x, just x. So that's what it means to be linear. Restoring means that it always tries to take us back to x is equal to 0. That's where it's happy. That's its equilibrium point. It's going to oscillate about that point. Finally, force. You guys know forces, right? We have talked about forces before. I don't need to define that one. But anytime we've got one of these linear restoring forces, that means that we've got simple harmonic motion. So this shows up all over the place. And even when we get a little bit more complicated, when you want to talk about sound waves or friction or anything else, that is still doable. This is the framework that we're going to use to describe all of those things. So I want to try this with a concept check real fast. I know we haven't talked about this a ton. If you have gone through the reading, you will probably already have an equation that describes this, but I want you to think about this for a minute. So I've got 2 identical blocks oscillating on different springs. I've got the red spring, the blue spring. And these are not pictures of those springs. These are the position graphs as a function of time. Which spring has the larger spring coefficient? Which spring is a little bit more stiff? Think about it for a minute. Try to compare it to some life experiences here. If you've got any playing around with springs. Okay, I'm seeing a few answers here. So let's compare two springs that maybe you've had some experience with. Take apart a pen, that spring in there. It's got not a huge force constant, but it snaps back. If you stretch that thing or you compress that thing, it's going to snap back pretty quickly, right? Compare that to a slinky, right? If you have ever messed around with a slinky or anything else, it's like a really bad spring. It doesn't work like another type of good spring would, right? Because the slinky doesn't really, you can't compress a slinky. The slinky is already pretty much folded up as much as it can be for compression, but you can stretch a slinky. And if I'm a little bit more interested in that stretching motion, let's kind of imagine the difference between the two. If I stretch the slinky versus if I stretch the pen spring, which of those is going to snap back quicker? Which of those has the larger spring constant? I'm going to argue it's not the slinky. The slinky, if it would even begin to snap back, is going to do so incredibly slowly. Right? They're really bad springs, is what they really are. Or really flimsy springs, I guess is what I should say, because you design the spring for whatever you design the spring for. But generally speaking, what we're looking at here is that the stiffer the spring, the faster the snapback to oscillating back and forth. The red spring is going to be taking it this time around, even though they're not at the same amplitude. Right? As it turns out, as I'm going to show you here in just a little bit, the amplitude that we actually pull the thing out doesn't actually make any real difference. Which might be a little bit misleading at first, but you'll see some equations that will hopefully kind of provide some evidence behind that. But the red spring is the stiffer spring. It's going to snap back and forth much quicker because it's a stiffer spring. So let's go ahead and take a look at the actual free body diagram. I said I really don't care about the forces in the y direction, and that's going to remain true. But so here's my block, right? I've got a normal force, gravitational force, no friction. So what goes on in the y direction? I don't care. What goes on in the x direction? That's something that's a little bit more interesting because we notice here that we are moving in the x direction. So there is an acceleration in the x direction. And what is that acceleration? Well, it's equal to negative k over m times x. Now that's a little bit interesting when you think about it. Because for something that's oscillating back and forth, these graphs that I'm showing here, I've got a particular interest in being able to map out where is this block at any given time. See, a lot of these things that we've been looking at so far, maybe we're interested in particular instance or anything else like that, but simple harmonic motion is essentially, we're very focused on what's going on the entire time because it's only limited to this tiny little space right here, right? It's not going from A to B, it's oscillating back and forth between these two little spots. So I have taken a little bit more of a keen interest in what's actually going on there. I would like to be able to plot out what that looks like. But the difficulty with that is that the acceleration that the block feels isn't constant. And this in itself is just, it's not something that we have really grappled with too much. We have looked at non-constant acceleration, I realize. We have dealt with it with energy. And that's fine in its own right, and we'll get there. But to actually understand what's going on with this motion, we really need to kind of grapple with what this equation is telling us. When we've been looking at things like gravity, we haven't been looking at how does the acceleration change. I've got two masses that are flying towards each other. I haven't looked at how the acceleration between those two changes. Even when we were looking at these things in a little bit more detail, when there was motion associated with the planets, we're specifically oftentimes looking at the cases where the acceleration was a constant because things were moving in circles. Now, we're going to focus a little bit more on getting the complete picture of our motion. So here's what we've got, right? Realistically, we might remember, it's been a little while, but the acceleration is the second derivative of position. Position, velocity, acceleration. Second step down from position on that derivative ladder. We know, then, that the second derivative of x is equal to negative k over m times x. This is a differential equation. A differential equation is any time I have a derivative of a function depending on that function. If the derivative of f depends on f, then we have a differential equation. To solve this, we need to figure out, essentially, we don't know what the function looks like. That's the whole thing. We understand this relationship between acceleration and position, but we don't actually know what position looks like, right? We want to be able to plot out position, and right now, I just have x. I don't know how to plot x. What is x versus t? It's meaningless to me right now. So what I need to do is I'm going to take this as my condition. This is what I know to be true. I need to find what function of x satisfies that. What function of x actually fits in? If I did, I don't know, x is equal to t squared, does that work? No, it doesn't. You want to go through and check it real fast, but here's the big sticking condition of what we're looking at here. We have something that is going to turn back into itself with a second derivative, right? And how do we actually find any of these things? Well, there's the tried and true model of guessing. See, if you have taken some of these classes like differential equations or Calc 2 or Calc 3, you might be a little bit more familiar with this. And I guess what we can really say is that it's educated guessing, but it's guessing is really what it is. It's what we have been doing for a very long time, and realistically, I don't want to change it anytime soon because it works out pretty well. We build up some good intuition about these guesses. I'm not going to ask you to make a bunch of these guesses. I'm going to tell you what my guesses are, and we're going to see if those work. If we have guessed correctly, we found the solution, right? If we have a good guess, if it works, perfect, we're set. That's all we need. So, and I've got a whole bunch of all of these details down here. It's not things that I want to talk about necessarily right now, but if you're interested in some more of those details, there's going to be things with that. If it's experiencing a force, yes, it is experiencing the acceleration. This acceleration is because of that spring force. So we give it the old college try. This up here, this is the goal. This is what we're shooting for. So here's what we need to do. I say, all right, I look at this thing and I say, all right, I take a second derivative and I arrive back at the original function, some constants on the side, and a negative sign. What functions do I know of that have essentially a repeat of themselves when I take the second derivative? And there are two big things that come to mind, maybe three, depending on how you want to call these. Technically, one of the solutions that I'm thinking about here is going to be sine and cosine. And you can make an argument that that's two separate things, but it's literally called cosine. Sine and cosine they're the same thing. They're sine waves. You don't call them different or anything else. There's an easy way to go back and forth between sine and cosine. We have seen before that the graphs are identical. They're just shifted by a little bit. So to say that it's sine or cosine, it doesn't really matter. One of those two, we're going to pick one and work with it. Let me just go ahead and say, let me take cosine. That's perfect. So if I guess a solution, A cosine omega t plus phi naught. Now, we need to pick apart, how did I get here? I said cosine, and now we've got all of these variables floating around, right? This is a little bit strange. But what I'm trying to tell you here is that there are some values that might be there that we are not entirely certain whether they would be or not. I think this is best done in an example, though, as kind of proof that this function works, and I can talk about those details. But before I jump away from this slide, I've got a question for everybody. Is there some other function that could do exactly what we need from sine and cosine here? I've already exhausted sine and cosine. Is there some other function? E to the x is a fantastic thought. But e to the x is not on its own quite enough. We need to do something special with it. Because, yeah, how do we find a function? How do we find an exponential that gives a negative on the second derivative? If we had done e to the, let's say e to the negative y, then the first derivative would have just been negative e to the negative y. The third then would have been, again, back to a positive. So that wouldn't have worked. But e to the iy suddenly does. And that's a mess. That is, I don't think I need to describe why. You put in some sort of imaginary value. If we would have taken something e to the iy, then by the second derivative, you would have had I squared. You would have had negative e to the iy as your second derivative. Putting in imaginary numbers, or complex numbers, if you have been taught that imaginary numbers are a bad way to phrase those, is absolutely a doable thing. And actually, as it turns out, e to the iy like this is effectively equivalent to sine and cosine. You can actually use those as substitutions. If you have done anything, I think in Calc 2 this gets covered, Euler's equation, which is e to the I pi plus 1 is equal to 0. I think that's the one. I might have one of these things mixed up somewhere or the other. But I think that's the equation right there. Euler's equation. It is a beautiful disaster. One of my favorite equations. It's such a disaster. But you can replace those things. That is the other function that would technically apply here, but I'm trying to tell you that those are technically the same function. It's just a different way to write sine and cosine. But anyways, my entire point here was that we should start looking at an example. I have given you, this is my guess. This is what I think works very well to satisfy this right here. Your job is to prove that it works. And to figure out, do any of the variables that I've listed here, a, omega, phi naught, do any of them need to have strict conditions to make it true? Is there something that we need to set omega equal to make sure this condition works? Work on that derivative. You'll have to take your x function, take two derivatives down, and then plug those into our differential equation right here. Take the next 3 minutes, give that one a shot, see what you can come up with, and then we'll look at it together. All right, so let's start taking a look here. I'm just going to do this one on this page, but here's what we're going to start with. I'm going to say, all right, to begin with, I'm going to write down my function. X is equal to a cosine omega t plus phi naught. Some random equation that I've just thrown at you that I'm telling you is the result of some clever guessing. And I can say that it's clever guessing because I didn't actually do that guessing, somebody else did for me. And that's all right. So now what we're going to do, we're going to take the first derivative of this thing. A is a constant. What's the derivative? Some function times a constant. Does the constant actually do anything? No, passes right on by. So I'm going to say, all right, well then A just kind of continues chilling there, not doing anything else. The derivative of cosine is negative sine. So let me go ahead and throw that negative sign out front. And then I'll put sine of omega t. And now I need to do chain rule on what's going on the inside of my sine function. I'm taking this derivative with respect to t. So phi naught, another constant, doesn't matter. Derivative of just a constant by itself is 0, so that doesn't make any impact. Omega t, omega is a constant, t is our variable of interest. So an omega is going to come to the outside. Okay, so that is my expression for the velocity. And if I want to be careful with it, I can keep going to this thing, right? And that negative sign, let's keep that going on. The A, still chilling. Omega, fine, we'll leave that there, I guess. Now, the derivative of sine is going to be cosine. No extra negative signs here. Omega t plus phi naught. Chain rule, once again, means that we're going to pull out another omega. So omega squared. Perfect. And that's our acceleration function. Now with this, we said that this acceleration is equal to negative km, k over m, times x. So let's plug in what we just did for x. X is a cosine of omega t plus phi naught. Okay. Now, this is why this a can kind of do whatever it wants to do. There's an a on each side of this equation. And this is one of those tricky things about guessing, because technically a being there doesn't matter. It can be anything it wants to. It could be 5, it could be 0, it could be 1, it could be 30, it could be pi over e, some stupid number like that. Any value that we plug in for a would be totally fine. It would satisfy these conditions. So we need to include it in our function because this condition does not say anything about what a needs to be. this is not a restriction on A. A is allowed to be whatever it wants to be, so we need to make sure to include it there to basically say, okay, well, this function, whatever it wants to start with, it's allowed to do that. Anything that shows up from A in the x side of things just shows up in the acceleration at the exact same rate. So I'm going to cancel out my A's. I'm going to cancel out these minus signs. We don't need those. And then I've got cosine of omega t plus phi naught. None of those matter either. Cross out those. What I'm left with is omega squared is equal to k over m. That is to say, omega is equal to the square root of k over m. Now, what do we know omega to be? We're familiar with this variable. What context are we familiar with this variable as? Radians per second is going to be the units of it. Sure. But I'm thinking of something a little bit different. Angular velocity is what I'm thinking of. Or angular velocity conceptually is what? On a conceptual level, when something has a faster angular velocity, what does that mean? Yeah, speed of rotation, how fast it goes around. How fast it goes around in a circle, that's an oscillation. Hint, hint. So is this. This is another oscillation. It's not an oscillation in a circle in the same way, but it's an oscillation back and forth. Omega is a measure of how fast we go through a complete cycle. So, this is basically saying how fast you go through a complete cycle is relative to the square root of our spring constant over the mass. So when we come back to this concept check, then we say, all right, well then the one that's going back and forth faster in the same amount of time must have the larger spring constant. Hopefully that all kind of ties itself back together here with some of our older concepts here. And I'm talking older like it wasn't just 15 minutes ago, but kind of tying all of these details together from all these different places. So where some of these things came in at, we knew from the very beginning that essentially we were looking at some sort of sine or cosine. And we said sine or cosine, it doesn't matter which one because they're the same thing anyways. At the end of the day, we just need something that fits into this equation and accounts for anything that might be there. And that's the trick, the anything that might be there. We're going to talk about this a little bit more next time. For now, hopefully it is satisfactory to look at what's going on with A, what's going on with omega. We need omega to be there, because if omega was not here, if it was just cosine of t, then square root of k over m would have to be 1 every single time. And we just saw we can take the same block and attach different springs to it. So I must have some variable that changes with k and m. I must have some variable that affects how far out I pull this spring in the first place. Phase constant is one more of those similar kind of things. It is something else that, what if I were to change what was happening here? But we'll talk about that a little bit more detail next time. You will see it in your reading, though. So, I do have fancy names for all of these things. And some of these names, you'll have seen before, actually. So, A is what we'll call the amplitude. And I've got a quick question for everyone. While we're right here, why did I choose cosine instead of sine? Why did I say x is equal to a cosine? Why didn't I do sine? Could I have? Sure. Why didn't I? Why might, and there's not really a definitive answer here. What guesses do you have? Why might I want to use cosine instead of sine? Cosine's value at 0 is 1. Okay, and what does that match with pretty well? So what I'm thinking here, and I've seen I see a few different ones of these things. Cosine goes with x. That's not a good one. Remember here, the cosine is not exclusively x. Keep that in mind. Cosine and sine depend on like what's going on. Sometimes in the unit circle, yes, that would be true. To compare a unit circle to x and y, the Cartesian coordinates, cosine would go with x, but that's really not why I'm interested in it here. And remember that cosine is not always necessarily at x in a lot of our problems. But what I'm thinking here is that let's go back to my original description. I pulled this thing out by some amount and then released it. So I started at my maximized value. I started at A, at 1, and then I released it. That's a pretty good reason I can think to get into this one. Cosine works out pretty well, but the fact of the matter is if you had taken this course somewhere else, somewhere that's not Miami, or perhaps you used a different book or anything else like that, you might find that they list the position as going with sine instead. And I want to tell you that it really doesn't matter which one you pick. You can do sine, you can do cosine. There's a little bit of a difference between the two, but at the end of the day, they're off by 90 degrees, and that's the only difference between those two. And we can handle that. There's a way to get around that. But what we are going to do as a standard for our class right now, I'm trying to tell you that we want to always use cosine for the x position, just because it's going to make everything a little bit easier. We're all on the same page. We all agree that it's going to be cosine for that position at the first stage. And then later on down the line, you go into some career that you need harmonic oscillators because harmonic oscillators show up literally everywhere. You can pick and choose whichever one works better. If you want to use sine then, perfect. If you want to use cosine then, perfect. If you want to use the exponential with an imaginary exponential up above, perfect. Probably not so great on that one, but any of those that you choose to do once you're out of here, totally fine. Just for this class, we are going to focus in on cosine. That is just going to be what we use. So that always means that velocity is going to go as a negative sign then. And now we see xv, this capital A that I use. If you have done differential equations, you will probably be used to seeing a capital A, capital B, capital C for the constants when you are doing your educated guessing for solutions. But capital A works out very, very well for us because it also means amplitude. Right? If we're going up and down and up and down and up and down, that peak is what we call the amplitude of the wave, and that amplitude of the wave is essentially where we released it from. Perfect. So now, omega is going to change its name ever so slightly. Notice that the units are exactly the same, but it's done like the little hat and the glasses with a mustache attached to it tries to disguise itself and call itself angular frequency now instead of angular speed, but at the end of the day, it really is the same variable. Still omega. Our old value, just regular frequency, f, we know that that relates to the angular frequency, even though we haven't seen that in quite some time. And we also might remember the period as being essentially 1 over the frequency. All of these things are things that we have seen before. I know it's been a little while, but hopefully this will all kind of come rushing back to you very quickly here. Right? When we first started talking about rotational motion. And it's, at the end of the day, the same thing. So, if we were to graph this thing out, here's what we get. I start by pulling out my mass and then releasing it. Right at t is equal to 0, that spot right there, that is my initial release. So it snaps back and then goes up and then snaps back and then goes up. And what we've got here, we can see represented on the graph is the period. So between this point right here and the next full cycle, that's my period. How long it takes to go through one cycle. How long it takes to come back to that initial position. So, why can I not represent, let's take this point and this point. Why is that not the period? Why does that not actually represent what I'm looking for? Yeah, I haven't actually finished my cycle. A sine wave goes up, all the way down, and then back to the original position. Cosine starts from the top, goes all the way down, comes all the way back up. So what we need here, to finish the full cycle, we need to have the exact same motion. We need to come back to our initial values for everything. It's not just that our position needs to match, because if only our position needs to match, then we could take any 2 points, this and this, and that's clearly not a full cycle, right? That one's especially weird. At least in the middle, we can kind of be like, okay, maybe, that's kind of sharing a symmetry, but like, Up here, no, not at all. So we need to have not only the same position, but the same velocity and the same acceleration to be considered a complete cycle. That is to say, if I want to start here, then I'm skipping this point. I'm going all the way till over here. That is my complete cycle, because now my position is the same, the direction going downwards and my slope, my velocity is the same, and then if we were to actually take that full next derivative, the acceleration we would find would be the exact same as well. So, whenever you're looking at a graph, keep that stuff in mind. Don't be fooled looking at the zero spots. But we could continue this description all the way down. We would say, okay, well, at its maximum, what is the most that cosine can ever be? 1. What is the most that sine could ever be? 1. So for both of these, we're essentially limited. We see these dotted blue lines at the top and bottom. If we're looking at our function here, or I guess I've got it on this page. No, I don't. I've got it on this page. The most cosine can be whatever omega t plus phi is. I don't care about that. I know that as it cycles through, the most it's ever going to be, this function is going to be a. That's our peak. The lowest it's ever going to be is negative a. For velocity, same argument. Sine, at its most, is going to be positive 1. At its least is going to be negative 1. That relates to a negative a omega and a positive a omega. Those two sides, those are the limits, the bounds of each of these graphs. But we'll notice here as well that when we've got a maximized position, and these things are ever so slightly offset because I'm very bad at lining things up. Let's try that a little bit closer. We'll even overlap these a little bit. That's fine. Overlap these just a slight bit, and notice what we find here is that at this position, we see that the velocity is 0. Maximized velocity when we have 0 position. And then, of course, we would see the same thing right here. And these are not particularly well lined up, but they should be. They're ever so slightly different. I think I stretched these things somewhere in the pictures. But we see these two are supposed to be lining up, essentially. Anytime we have maximized position, we don't have any velocity. Anytime we have maximized velocity, we have 0 position. It just goes back and forth. So, concept check here. Keeping all of that stuff in mind. This spot that I've highlighted right here, it's got a velocity, it's got some force. You are given the position graph. What do we know? Looking at this graph right here, what is the velocity? What is the force? Take the next 20 seconds. Think about it. See if you can come up with an answer. All right, any guesses here so far? D, one guess so far? So let me talk through how I would think about this. First, they say velocity first, so my eye is drawn to velocity. Let me think about velocity. Velocity is the derivative of position. That is, on a graph, the slope. At this point in particular, right down here at the very, very bottom peak, my tangent line is flat. A flat tangent line tells me this answer, this answer, this answer cannot be correct because my velocity should be 0. Now, the only thing left I've got to find is what's going on with my force. And I might remember, for any time, there's 2 different ways to think about this. First, I could think, hey, I know it's a spring. I know a spring force goes as negative kx. So if I'm plugging in a negative x, then the negatives will cancel, and I end up with a positive force. The other way that I could think about this is what direction is my position about to go? What is it trending towards? In a little while, it's going to be positive. It just turned around. It is maximally negative right now, But if I look just a little bit later, it's going to be more and more and more positive. That tells me that the second derivative must be positive, right? This is our turning point here. In our turning point, if the acceleration is positive, then it's an upwards curve. The second derivative is positive, the acceleration is positive, the force is positive, the same graph every single time. Two different descriptions to get to the same answer. The force should be positive. All right, so let's keep chugging right along. I want to try this into a problem here. So some of those random named values that I was talking about, period, frequency, angular frequency, amplitude, and maximum speed, all of those things considered together. I'm giving you a little bit of information about some sort of air track glider going between two different points. That's not zero. Think about it a little bit, though. You've got some details here. What I want you to find is those 5 values, a lot of small steps. Take the next 3 or 4 minutes, though. See what you can come up with. And then we can come back and take a look together. Okay, so how's about we start taking a look at this? I've got some interesting details on this one. Right, this thing is clearly not oscillating around 0 like everything else that we have seen so far. So, what do we do with that? Well, I don't like that much myself. How's about we just shift it to be 0? Right, what does it matter? If it's supposed to be going back and forth between 10 and 60, sure, that's fine. Let me just do what I always do and say, I'm going to call this spot 0 instead. Let's try it. Let me show you what I'm talking about here. If we had plotted this thing out, and we were told that it looks something like this, and let me do this. I'm going to put my x-axis right there. Go back to this one, and we say, all right, well, it was oscillating back and forth. We said it started from 60. It goes like this, all the way down to 10, and then back up, and this is exactly what a sine wave is supposed to look like, right? And we said, okay, that's fine. Well, this is 10 relative to that, and this is 60 relative to that. Whoops, 60, like that. But I'm going to say, forget it. I don't like that. I don't want to deal with that being right there where it's at right now. That's not matching anything that I've been doing so far. So here's what I'm going to do. Erase that. We're doing the problem, right? We can shift this wherever we want it to be. I'm going to put this thing right smack dab in the middle so that it looks like everything else we've been doing so far. Now that it's right there in the middle, what do we say for these new values on the outside? 10 and 60 have become what? My smack dab in the middle spot became 35. So my top is now positive 25. My bottom is now negative 25. Perfect. So anytime you see some sort of oscillation like that, just say, okay, well, that's fine, but that's like an oscillation up there. And I don't have equations for an oscillation up there. I've got equations for, whoops, plus 25. I've got equations for an oscillation right around 0. So if we shift it to be right around 0, no big deal. That's fine. Doesn't matter a bit. So now we've got some other details with us. With this in mind, we look at this thing. What is our amplitude? Right off the bat. I know that's part D. What is our amplitude, though? What do we see off of this graph? 25, yeah. Right? Amplitude is the measure from the peak down to 0. So 25 down to 0. Because we're going back and forth between the positive A and the negative A. So it's not the full 50, because that would imply going from positive 50 all the way down to negative 50. We're going from plus 25 down to minus 25. Right in the middle is 0. Amplitude is positive 25. So we'll start with that. Part D already solved out for us, right? That's a good sign for the rest of this problem. Now, there's one other detail that we've gotten from this. We were told that it makes 10 oscillations in 33 seconds. So if we wanted the period, then that's essentially how long does one oscillation take. I can take my total time it took divided by 10 oscillations. So this is seconds per oscillations. Now it becomes seconds per one oscillation. There's my period. With that, we can keep moving right along, right? We need to find the frequency. Frequency, nice and easy. The inverse of the period. Plug those numbers in, and what do we find? Oh, this one's a little bit nasty. This is 0.303 hertz. Is the unit for that. Angular frequency, same deal as before, right? We can do that relationship between all of these things. We saw on this one, omega over 2 pi. So if I just take my frequency, I multiply it by 2 pi. Times the frequency. Now, there's two ways that I could write this one out. This is kind of I haven't provided any sort of context for this thing quite yet. So realize that when I say this. But I could write this out as 0.606 pi radians per second. Or we could just plug in pi so that this thing would become 1.90 radians per second. They mean the exact same thing. Either of these descriptions would have worked perfectly fine. It's just sometimes what we're going to plug in are essentially just, you might see pi floating around at the inside. Sometimes we do that because it's a common thing, and usually pi is one of those numbers that it's oftentimes best to leave it just as pi because it's technically an infinitely long number with an infinite number of non-repeating decimal points. So it's just one of those things. Sometimes we'll write it out as pi, sometimes we'll write it out as the full number. It doesn't really matter. Nothing we do cares about that precision so much. But we have now 4 of our values. The very last one that we were looking for was the maximum velocity. Maximum velocity. There's a couple different ways that I can imagine this, but probably the best one. What did I say for this from before? I think probably the best way to imagine what's going on to the maximum velocity here is, let me just look at what's going on with my description from before. But look at this thing. We said the biggest that sine could be is 1, or I guess the smallest, -1. So our maximum velocity, the peak of this thing, is just going to be a times omega. We've got a. We've got omega. V max is equal to a omega. We plug those numbers in, and I didn't calculate that out last time. What did I say this thing was actually supposed to be? I got rid of it again. This is the only number I didn't write down for some reason, and then I didn't write it down a second time in a row. So I can leave it as centimeters. This should have been something like 47.5 centimeters per second. And there's all 5 values. Just a lot of little steps, right? Not anything necessarily really big in solving or anything else like that. Just a bunch of smaller steps to find a bunch of individual values. In that case, let's keep grooving right along. It says 47.5 for question 3 on the in-class is incorrect, because question 3 is not this problem. And the only reason I know that is because we made the exact same thing in the last lecture as well. I know it's similar, but we haven't done that whiteboard problem yet. We're getting there. Vmax is equal to a times omega. Yes. That is just true because sine can be anything between 1 and -1. So the most that the velocity could ever be is a times omega. Actually, in the last lecture, it got so bad that I absolutely believed that I screwed up the problem. I had to go in and check it myself before somebody pointed out that, yeah, that's supposed to be 15.3, not 15.2. So we're getting there. We'll get there soon. One last thing that I've got as we're talking conceptually here about a lot of these things. We might remember that springs have energy with them, right? Which is hopefully not something new to us at this point. Springs have a little bit of energy. So too does velocity have energy associated with it. Springs were conservative forces, and assuming that there's not friction or anything else preventing our motion, energy is conserved. Right? And this is why, technically speaking, something like this doesn't actually work, because perpetual motion is not a real thing. There's air resistance, there's friction, there's like tensile forces inside of the spring. There's a number of things that are stopping this from actually happening, but for all of our simple harmonic motion, the model that we're creating to use in the future is essentially going to be that there's conservation of energy applied at all times. Right? If I take my kinetic energy and my potential spring energy, it should be a constant for this entire thing. even if I'm in a scenario where all of my kinetic energy has disappeared and it's all in spring potential, or in the opposite case where we only have kinetic energy, it doesn't matter what state we're looking at, the entire time my energy should be constant. Which is really useful because that means that if we know anything about the energy, then we can immediately use that to help solve out for what our amplitude is, because our amplitude is our maximum displacement. It is when we have only potential energy and no kinetic energy. Vmax is when we only have kinetic energy. So if we understand what the energy of this system is, we can use that information to quickly find some of these important details. For example here, if we were to actually plot these things out for all different positions, we would get an energy graph that looks a little bit something like this. This is basically saying, hey, the combination of spring energy and kinetic energy should always be a flat line over top, even though the values going into that are little parabolas. So it's a nice little convenient thing. Right? That nice looking curve right there. It's got everything we need for it. And then the plus and minus A are called turning points because, again, it's where it changes direction. It was going down, then it reaches its turning point. It has stopped going in the negative direction, and now it's starting to move in the positive direction. Right? All of that good stuff that we have seen before from all of our old calculus and pre-calc details. So I've got one last question for you here. Think about it a little bit. A 300-gram oscillator has a speed of 95.4 centimeters per second when its displacement is 3 centimeters. State 1, we've got a velocity, we've got a displacement. State 2, 71.4 centimeters per second when its displacement is 6 centimeters. What is the amplitude and maximum speed of this oscillator? I want you to take the next 4 or 5 minutes to work on this one, and then we'll come back together and see what you got. Okay, let's go ahead and start taking a look at this. And the question, what is the phase constant? How do we calculate it? That is something that we will grapple with a little bit more next time. Or it should be in the reading as you're talking about it. It's more or less, realistically, it's where we start. Do we start at the top? Do we start somewhere else? That's the only difference between these two. If we move our starting point a little bit, that's what the phase constant's doing. Not anything else other than that. So let's go ahead and take a look at this problem, though. We've got some details here that we probably need to write down. First of all, we know the mass is going to be just 0.3 kilograms. And what I'm going to do here is I'm going to put everything into standard units to start, just to make sure that we're not messing up anything anywhere like joules to millijoules or something stupid like that. So let's just go ahead and focus on standard units, and then at the very end we can convert these back into centimeters, just because that way we're not, we're not messing around with anything that might be a non-standard unit in the middle of solving, anything that might screw up our order of magnitude or anything like that. So I'm going to say state 1. That is where V1 is equal to, this was our 95.4 meters per second, or 0.954, or 95.4 centimeters per second, 0.954 meters per second. We said that's our velocity, and our displacement at that moment in time was 3 centimeters. And then we say state 2, we were going at 71.4 centimeters per second, so 0.714 meters per second, with a displacement of 0.06. Now, I think the easiest way to approach this at this point is to say, okay, I don't have a lot of detail here. I don't know anything, nothing I see here I can immediately extrapolate any information in particular. I don't know the spring constant. I do know the mass, but without the spring constant, I'm kind of out of luck on that one. I don't know anything about the amplitude. I don't know anything about the time. I don't know anything about the frequency. Yikes. It's a lot of details we don't know, but that's all right. We don't actually need them. What we're going to do instead, we're going to say first, all right, I don't know the spring constant, and that's going to be a problem, but I do know these two separate states. So let me think about how much energy each state has. Highlight these two, and what I'm going to say, all right, well, in our first state, we've got some combination potential and kinetic energy. 1/2 mv1 squared plus 1/2 k x1 squared. That should be equal to my energy in state 2. mv2 squared plus 1/2 k x2 squared. So the reason that I was interested in this is because looking at this, I know the mass, I know each velocity, I know each displacement. I don't know my spring constant. So this is the perfect opportunity to solve out for that. Solving out for this spring constant right here, what we're going to do is we're going to say, okay, let me move all of the kinetic energies to one side. Let me move all of the potential energies to the other side. So I'm going to say 1/2 m, and this will be, I'll do kinetic energies over here. So this is v1 squared minus v2 squared is equal to 1/2 k x2 was already over here. So that's positive x2 squared minus x1 squared. Okay, we don't need those 1/2, so I can get rid of those. I'm going to divide over by my x's, so that to that. This is going to become v1 squared minus v2 squared divided by x2 squared minus x1 squared. Keep track of the algebra on this one because it's easy to get those flipped. Times the mass is equal to my spring constant k. We plug in all of these numbers that we know, and this is exactly what I'm talking about. This is going to be in standard units, 44.48 meters, newtons per meter, is what I should say. So that's a good reason why we did need to calculate these with meters and meters per second, because otherwise we would have found some weird unit for the spring constant. We avoid that problem. We just know we're in standard units the entire time. So this is a big step, right? I don't want to kind of make that smaller or anything else like that. This is a really big step. Now that we understand that, now we can go back up to either one of these equations, this one or this one, and we can say in both of these cases, this is the total energy. And now that we have K, I can actually calculate what that energy is. I can say that E is equal to the both of these. Plug in the numbers for either one. It should give you the same result, and that result should be something like 0.1565 joules. That is our total energy of the system, and I'll even do energy total, is equal to 0.1565 joules. Now, I can imagine that, all right, well, this total energy is the total energy no matter what state we're in. If we are exclusively in spring potential energy, it's still the same amount of energy. If we are exclusively in kinetic energy, it's still the same energy. Same energy every single time. That goes there. That goes also there. Same way. We know K. We know M. 1/2 is hopefully nothing new at this point. That means that the amplitude we should find is 0.0839 or 8.39 centimeters. Final conversion back into our centimeters. Vmax, similarly, comes out to be 102.2 centimeters per second. And there we are. All right, team. That's all I've got for the day. Do remember, we have an exam coming up here pretty soon. So I would recommend go ahead and start looking at some of that old material. It makes everything a lot easier if we look at it slowly over time, a little bit each day, rather than trying to cram it in the last day before the exam. I promise. Opens up a lot more time to ask questions, all that good stuff. But until then, I will see you guys next time. Thanks for being here.